So introduction to PCA, principal component analysis. So today's topic is really this like analytics part, specifically the statistics part. But also this algorithm or this technique can be used to actually visualize the data. So not the typical visualization that like we go like aggregating the data and using the charts to visualize, but also use the algorithms to be able to visualize the patterns that like typically like you couldn't uncover. So I think it's sort of like this is about analytics, but its goal is kind of like visualization. And if you allow me to say it's not just visualization, why you're visualizing, it's more to do with how you can communicate that insight with other folks or to yourself. Okay, so here's a high level description of the PCA, which is number one, this is unsupervised statistical learning. In some people call it like machine learning. The difference between machine learning and statistical learning is not as important in this context, but it's supervised. So it's not like you have the answers and then like you want to map the data to the answers and something like that. This is like you have the data and then like have the algorithm find the patterns that is useful to you. And so second is that this is commonly known as a dimensionality reduction technique or method to reduce the dimensionality of the data when you have like let's say like 50 columns or something that, you know, about your customers or countries or employee, you know, but by using this type of technique, you can reduce the dimensionality into a few that is enough to still hold the information that original data had. And then the third point is that I think this is really the topic of this today's seminar, which is helps us to visualize the relationships between the variables and also the characterize the subjects of your interest. For example, customers, maybe employee, maybe the products or countries and so on. So that's really PCA in a nutshell. So I want to actually get into like the detail of the PCA, which I'm going to explain after this, but I want to make sure like everybody's on the same page. So the two big concepts, number one is the variation, or sometimes we call it variance. And the other is the correlation. The variation, the data varies, right? So you never have only one single value. Let's say like we're talking about the salary, employee salary or something. And then average can be 6,000 something. But you know, some people make like 1,000, some people make like 15,000. Data varies, so the variation is from like the low to the high. So this is like a variation. And then, you know, when you visualize the data by using histogram, and then like, you see the variance better. This is a topic though I covered in the previous seminar, which was about like visualizing the data in an exploratory data analysis context. So if you're interested in like variance and correlation, you might want to check that out. But so this is about here's the variance we're talking about. And then when you have the variance, the problem is that variance brings uncertainty. Right. So like if you ask, let's say like, hey, what's the income in this company? And then like you can give the average, but the average doesn't really give you the whole picture. And therefore it can be 1,000, it can be 20,000. So that's the uncertainty. Then you want to find a correlation that whatever the variable or something, some other columns or whatever you call it, that is correlated to monthly income. And so like this, right? So when you have a scatter plot and working years happen to be correlated to monthly income, then like you can see almost like you can draw a straight line. Each orange line represents each employee, for example. And then once you have this, we've discovered this kind of relationship, and then that helps you to answer the questions of like, hey, what is the monthly income? Well, like it depends. And if you work for like 20 years, then your monthly income will be like around $15,000 or something like that. So what just happened is a correlation reduces the uncertainty caused by the variance. So the variance and the correlation come sort of like together. So and it helps. Like, I mean, like it can be used in the same sort of like in a data analysis, a strong sort of weapons or tools to find the patterns and also answer or like predict and explain, what it is in the data. So one thing before I want to make sure is like correlation. Correlation has a strong correlation and then no correlation. And when in a strong correlation, like you can have like a strong negative correlation and a strong positive correlation. The left-hand side spectrum is a strong negative correlation. One variable increase and the other variable decrease or vice versa. And if the right side of the spectrum, the strong positive correlation is one variable increase and the other variable increase. And one variable decrease, then the other variable decrease. So like in the same direction. And then the center is a no correlation. When you look at it, even like visualize, you can't tell like which way like you can draw the line. So those are like no correlation. So I want to make sure like we are all on the same page in terms of like understanding or interpreting what the correlation is. Okay, and typically you use a heat map, right? One way to express is like basically in the exploratory or in R. Exploratory is UI for R, so like we use a lot of like R functions behind the scene, and then so one of the functions or one of the algorithms we can use is a correlation algorithm. And then when you use it under the analytics view in exploratory, then you get this type of the view, which is called heat map. And then like in this case, the red color, the higher, darker the red, the higher the positive correlation. And then the darker the blue is the higher the negative correlation. And then when you see the kind of between like a gray, that means there's almost like no correlation there. So, okay. And then like you can notice though, like one thing, it's might be a little bit, I don't know, maybe this is something that like I'm gonna just quickly go in here. Here, go to the analytics and then let's see the correlation by columns. Then I'm gonna select all of the variable. And by the way, this data is each row represent each employee. Okay, and then there's like an age, monthly income, working distance from home, and a job role, and so on. Anyway, so I'm going to give all the numeric variables because correlation can find the correlation among the numerical variables. And then like, you get this type of the heat map. Now, like when I see here is job level and monthly income, right? So the value is 0.95. So it's very, the correlation value only between like -1 to 1 and 1 as the highest correlation, highest positive correlation. So 0.95 is pretty like good or high. So the job level monthly income seems to be correlated, very highly correlated. Now what that means, so like if I go to like scatter plot, and if I job level at the x-axis and the y-axis and the monthly income, and then I get the chart like this, and then it turned out job level has only like 5 values, so it's almost like kind of looks like category. When you have the category and then like comparing against the numerical variable, you might want to try also the box plot. Which way is fine? Either way is fine. Like whatever works for you. And I'm going to switch this x-axis numeric calculation to, instead of like categorizing the numeric, I'm going to just present numeric as a numeric, like a numbers and the original number. So it's like a 1, 2, 3, 4, 5. That's a job level, and it looks like you almost like you can tell, like once you know the job level, then you can answer like what's the range of the monthly income better. And it's almost like I want to say, like in this organization, the monthly income is decided, or salary is decided based on the job level. So these two might be almost like some kind of rule. It's not just randomly. It's probably like if you have to get to the certain level of job income, job level in order to get the certain amount of the monthly income. So this is what the 0.95 correlation being just visualized, right? So let's go back to the slide. So now here's the question. So when we have a set of variables, like in this case, we have like about like 30 variables. When I say variable, which is basically the similar, basically the same thing as the columns in the table data, or attributes to describe, in this case, employee. So when we have a set of variables that are highly correlated, then do we need to keep all of them? Let's say like we have a job level and the monthly income. Do we always have to think about like both of them? Especially let's say like when we build like a statistical learning or like machine learning model or prediction model, do we need to have all, two of them together? Or like even like when we try to understand, let's say like employee, like how, you know, the characteristics of employee, like what are the groups, different types of groups like in this organization, and then can we describe them by using some of the variables? Do we have to say like, hey, job level is this and monthly income that, and then like job role is this or the gender is this? Do we need to keep all of the variables? And then another question is that do we need all of them to explain the characteristics of the subjects of our interest? In this case, employee. Do we need all of them? So, you know, probably like because this seminar is about principal component analysis or PCA, so probably like you're already answering questions. But let's look at another data. Here's the California election 2016. It's a little bit old, a few years ago. But this is about a ballot measure. So there were like I think it was like a 17 ballot measures. And it's a California's funky state. So we do, I live in California, so we vote for kind of fun stuff. So that was a year we were voting whether smoking marijuana is can be legalized even for like a luxury, not luxury, for having fun. Um, or like you want to ban on the single-use plastic bags because we are very sensitive to the environment and stuff. And also like because California is so big, like Northern California, Silicon Valley, and Southern California, the Hollywood media and stuff. So there was an adult film industry big there. And so therefore like we care about like if the actors should wear a condom or not, that kind of stuff. So again, it's a California funky state. So we have various different types of measures we voted for or voted against. And if we visualize this data, so now like each point is each county. Like we have about, let's go into the chart. I think that's probably easier to see and go to the chart. Hope I still have it. Okay, cool. Very cool. So there was 58 rows. So that data right now is, so each row is each county. So we have 58 counties in the California state. And then 19 columns, and the 2 columns are not measures. So like basically 17 ballot measures. And then if I visualize by using a scatter plot, and then like x-axis, the ballot measures, and y-axis, the yes ratio, like how much of the percentage of people who voted for. Okay, so now, for example, let's say like look at like, this like marijuana legalization ballot measure, and in San Francisco support people in San Francisco, like 74% of the voting people in San Francisco supported this measure. And for example, opposite end of the spectrum, the 44% of the people supported. That means that 56% of the people against it. So even like the county who went against it is like, you know, it's kind of almost like a 50-50. So anyway, like we can visualize like this. And then like from here, what we can see is, this is actually kind of funny because San Francisco is always at the top for most of the measures. And then look at this one, like this is like a firearm ammunition sales. So this is to make harder to buy firearms or guns and pistols, and I'm not sure it's a pistol, but guns or whatever. So here is like this, some of the counties like 0.2%. That means 80% of the people who went against, they want to keep the guns, right? And then this is a county in a very mountainside, so they probably like there are more people who loves hunting and so on. And then here, San Francisco is like only 15% people said no, and 80%, 85% of people said yes. Let's make it harder to buy the guns. Anyway, so by asking these like basically 17 measures, do we need all of these 17 measures? Because maybe some of them are related. So let's say, for example, let's look at San Francisco. San Francisco basically strongly support. And then also like the English proficiency, strongly support. Look at this like a cigarette tax, which is the increases the tax for the cigarette, strongly support. So, and then like you can also see this like a Democratic is blue color and a Republican county. This is based on which presidential candidates they voted for as a majority. So at the time that Donald Trump was a Republican and Hillary Clinton was a Democratic. So so it looks like a blue counties and orange counties. And then we can see like usually blue counties at the top and orange counties at the bottom. And some of the measures that goes opposite. So blue counties at the bottom and the orange counties at the top. And then some measures are probably, we don't really see much difference. It's either way, something like this. It's kind of like, it's not necessarily like a Democratic Party counties tend to say more yes than Republican parties or something like that. So maybe we can say we don't need to keep these 17 measures for analyzing the data or understanding the characteristics of each county. We can see, we can find the correlation between correlation among the variables. And when you, again, like this like same thing is like a heat map, right? And then the darker the red is highly positive correlation. And then the darker blue is a highly negative correlation. And we can see like a bunch of red here and then like a few blue. So that means like these, for example, red color variables, probably like we don't really need all of them. We need just like pick one or two. And that might be good enough. So let's say like if we pick like cigarette tags and firearm ammunition, and then present visualize by using a scatter plot and then very beautiful coordinated chart. And we can just, you can just draw the single line and then almost like most of the counties are along this like a line. And then again, like San Francisco is very high up in the right side top, and then like the left-hand side bottom is the Modoc and Lassen. Those are beautiful mountain counties, which probably they want to. Anyway, I don't want to go in detail, but we can present like this. And then now, if we keep all those 17 variables or measures or variables, that means we want to explore all the combination, every single combinations. And under the analytics views, correlation analytics, there is the tab that you can click and then get this view. But like it's just like sort of like confusing. And then do we really need to check every single combination and then try to understand like what's going on? So again, coming back to this question of do we need all of the measures? And then like I said already, maybe all we need is the 3 measures. One type of the measure is the Democratic counties are overwhelmingly supported, which means that Republican counties are overwhelmingly not supporting. And then another type of the county is Democratic counties are overwhelmingly not supporting. And then the last type of the measure is that Democratic counties don't give poop, right? Or like Republican Party counties who don't really care. And then so, or maybe like it's not about a Democratic Republican, it's something different. So the fewer questions or think about like you're building a product on a web page or something, like you want to do the survey, and then you can come up with like a 10 or 20 questions and asking your users to answer the question. Probably they're not going to answer because they're busy. So therefore, like the moment they see 10 questions, they just go away. But if they see only 1 question or 2 questions, you will get higher chance that they are going to answer. So therefore, you want to find like a few set of questions. Those are essential questions. The same thing in the California election board stuff. Even though like we know like there are only a few types of questions, but you have to ask all the questions, right? Because this is a democratic country. But if you have the product, the business, you can actually decide the fewer set of questions. And then that's good, but also let's say like you have the data. There's not necessarily like just survey or even like the employee data. Like you have like a different type of attributes like age or job role or monthly income and all all that. And then if we can represent that data with fewer variables, not with a 17, not with 50 variables, if you can represent the data with, let's say, 2 or 3 variables, then it makes it easier to visualize a relationship in the data or find a relationship in the data. And that makes it easier to discover and understand the relationship or characteristics of the data. And then remember, when we visualize, typically we're visualizing a two-dimensional space, like X and Y. And of course, you can visualize the data in X, Y, and Z, or you can visualize by using the color and the size. So you can bring a lot of dimensions if you want. But typically, like we're comfortable and we're good at finding patterns when the data is presented in the 2 dimensions. So therefore, when you have, let's say like 17 or like 50 variables, it's very important, very critical to try to sort of like a compact and then come up with like a few essential variables, then you can visualize and you can understand the pattern. So that's what the PCA is really about. Okay, so the PCA, again, it will generate the new set of artificial dimensions. We call these components that are created in a way that they're not correlated to one another, and then that can carry as much information of the original data as possible with fewer dimensions. So how does that algorithm do the job? So first, when you have the data, this chart at the bottom is basically kind of like a two-dimensional and make it look like three-dimensional, but it's a really two-dimensional, right? But let's use this as an example. And then, so let's say like when you have the data and it just, and then it try to find a center point, like a center of the data. And from there, it tried to find which direction is the highest variance. Right. So in this case, if check out this like a number 2 chart. That direction is the highest, or if you draw the line to cover from the end to end, that is the longest direction. And then that becomes the first component. And after that, it tried to find a direction that is orthogonal, that is not correlated at all to the first component. So usually, basically, think of it on a two-dimensional space. It goes like 90 degree. And then, but also still in that sense, in this case, for example, if you just think of it, this is like a three-dimensional. It can go 360 degree, right? So basically, you find a 90 degree to red direction, but still, like you can go to many directions. So now, if try to find a direction that has the highest variance, and that becomes the second component. And it does the same thing for to find a third. And in order to find a third direction, you try to find it so that this third direction is going to be orthogonal to the first and the second. And then, but also has the highest variance. And it repeats this until the last component. And what is how many number of the components this algorithm is trying to find? Well, when you start with the 17 variables, the 17 columns, then you try to find 17 components. When you have 50 components, 50 variables, then you try to find 50 components. Okay, so but typically the more components you have, and if you keep going, then you start basically like having sort of like the components that doesn't have much more information. So like usually the first one contains a lot of information on the information on the variance, and then the second still has a little bit, and then like let's say like 4 and 5 and 6, and it probably start having like just a little bit of variance there. So it has the information, but it's not that as important typically. So okay. So, so that's really the nutshell of the PCA, and you know, there's a more complicated mathematical concept around the you know, formula, but I think it's the best way to understand this PCA, how it works, is just to do it. So I'm going to use these 3 examples. Number 1 is US baby data. Second is California election data, and then third is the employee data that so the second and third we already saw it. So let's get into it. So number 1, US baby data. And so this data, here we go. So this is a US baby data. So where is here we go. Each row represents each baby. Oops, there we go. Yeah, each baby, and then like the baby was, you know, born in which month, and is that like a twin or triplet or single, which state, and what was that? What are the father and mother age, and also there is information about like you know, how many pounds of the weight of the baby, and then let's look at this like a mother and the father age. So this is the first example. So I'm gonna kind of start kind of gradually. Okay, so like we're gonna focus on this mother age and father age, and we know mother age and father age is sort of correlated, as you can imagine. So let's say like mother age and then the father age, and this is a scatter plot. So it's kind of goes like this. So like mother age, higher the mother age, and then probably higher the father age, and vice versa. Okay. And now, so we are basically representing this data, these babies, by using these 2 dimensions, which is mother age and father age, right? So now, let's say like if we want to reduce the dimensionality, we have only 2. That's kind of weird, I know. But let's imagine like if we want to reduce dimensionality, or if we can run the PCA, how we do it. So like here, I'm gonna just kind of show the linear regression trend line. And that basically goes in a kind of a center, right? So if you're interested in linear regression, like I actually did a seminar a few weeks ago, so check out the online seminar page. There's a video and then video recording and slides as well. But anyway, so here, so basically like when you look at this trend line, and that basically tell you how these 2 are correlated and so on. But more importantly, basically by just looking this line, like we can say like if any babies, these dots are kind of like closer to the higher end of this trend line, then probably like mother and the father's age are both higher. And in the opposite way, here is probably like mother and father's age are younger or smaller. Right. So PCA is kind of like doing similar things. Basically, this can be the first component. And it happened to be in this data, so this direction, like the left-hand side bottom to the right-hand side top, seems to be the sort of kind of the longest. And might not be technically precise, but it's kind of like just looking at it, seems like this direction has the highest variance of the data instead of like this way or that way. So I just wrote something here. So this is what we have. And if we rotate this, so like that scatter plot, and then now we have the trend line, and try to make the trend line as horizontal, then we have like mother age and father age is kind of going kind of cricket directions now, right? And then, so PCA is basically going to do very similar thing, okay? And then once you get this, then like we can start understanding the data in a very interesting way. So to do the PCA, so go to the analytics. Now I'm gonna create a new analytics here, and then select the principal component analysis bracket PCA under the type. And then variable here, like I'm gonna select only mother age and father age. You probably are not gonna ever do this because it's kind of stupid to try to reduce the dimension when you have only two. But this is to just explain how to interpret the result that you get from this PCA analysis. So if you click OK, and I'm gonna just run it. And here you go. So it's basically the father age and mother age. This is not 90-degree right now. So that's because I think this is the x-axis and y-axis. Like let's say like y-axis ranging from -4 to 4 and x-axis ranging from -3 to 5. So that's why. So but when you have the same exact scale, it becomes closer to like 90-degree. But so used to be, think of it like in the scatter chart, this zero line, horizontal line can be that trend line. Okay, so now how to understand this? So basically like you have this x and y, and what is the x? Well, like x is sort of like kind of like a correlated correlation line or trend line in a way, but also represent the mother and the father age. So like both father age and mother age increase, then like, I mean, x-axis increase, that means you can guess like father and mother age increase. An opposite way, when you go lower on the x-axis, that means father age and mother age decrease. Okay, and then what is y-axis? Well, y-axis is interesting. So this is where like I'm gonna start bringing the slide again. Okay, so now basically we have two, I mean, x and y, those are the dimensions. But also the cool thing about this chart is that like you still have this father age dimension on this xy axis plot. And then like you still have mother age dimension all presented here. And then when you see these lines, original measure, in this case, father and mother age, always start from zero, like a xy 0 point. Okay, and then zero doesn't mean father age zero. It's just that when it's 0 point, that means that's the average of the father age or average of the mother age in this case. And that means the opposite direction. If it goes lower side of the spectrum. And the same thing for the father age as well. When you go below the 0 point, and that means the lower side of the spectrum in this case. So there are a lot of information already here. So we still have looking at, and each dot is basically that each row, in this case, a US baby, not US baby, it's like a baby. Okay. So, and then this is a PC1. PC1 is a component, first component, and that has the highest variance in this data. And then like high is, you go to the right and high, and then when you go to the left is a lower values. Okay, and then the PC2. And then when you go to the component importance tab, then that's where you can see like how much of the variance, how much of the information is being captured by each component. In this case, again, we have only two components. And the first component has close to 90%. And that's because that contains basically like a father age and mother age information pretty well. And then something that is still not captured by the PC1 are captured by PC2. And a combined PC1, PC2, you have 100% of the information. Okay. So now when you see something, let's say, like let's take a look at this baby here. And then I also created one column, like combining mother age and father age together, and then I assign that to the label. So therefore, in the pop-up, you can see this is like a mother age and father age. So like a 42 is a mother age and a 48 is father age. And then when you look at this guy, this baby, whose father and mother age both are high, right? Both are higher age. And that's probably more like kind of intuitive at this point because father and mother are kind of like a higher side of the spectrum. And the same thing is only on the opposite way. When you go to the left side on this like x-axis, then both of them, like mother and father age, are low. And then you can see like mother age is 15, father age is 16. And then at the center is mother age and father age. Both of them should be average. So like when you pick one of them, it's very closer to the 0 point, and the mother's age is 27, father age is 30, and then both of them very close to the average. And then now like we remember like we still have this like a father age, mother age dimensions here. So that means let's pick one guy here, one girl here, one baby here, and then this baby is whose mother is 17 and the father is 36. Why is that? Because like this red line is a mother dimension, and it goes the right hand side or right hand side bottom, bottom direction, the higher. The opposite way is lower. So therefore, this dot is kind of closer to the lower side of the mother age spectrum dimension. Therefore, the 17 is like a much lower than the average. On the other hand, the father age, like 36, that's because the father age dimension, think about it like 0 is the average, then like that place looks like kind of higher side of than the average of the 0 point. So that's why it's a 36. And then when you pick another one here is, again, this one is on the red axis, which is the mother age measure, which is like a 36, but because higher than the 0 point, and in this case, kind of weird really, to say, but it's higher because kind of towards to the right hand side bottom compared to the 0. But father age here is lower than the average. That's why like father age is 22. And then when you pick here one, this one is very closer to like kind of end of the father age spectrum on the right hand side top direction. And then that's why the father is 63. And the mother is kind of hard to see, but it's actually, it says, I think it's like a 31 or something like that. Wait a second, I'm not sure here. So let's pick, for example, something like this. I'm gonna assign this column, and then let's take a look. One we're looking at here. So like let's say like something like this is this I also brought like a weight. So but the focus on like 32 and 60. So like 32 is mother age and 60 is a father age, and that's because again this is like a 32. Here we go. Yep. Okay, 31, and that's because it's older than that. This one, this we are talking about this dot, and then older than this like average line. So that's why it's a 31. So okay, so we can kind of start understanding like, what is each dot, or like, why those dots, I mean, in this case, the babies are located, and that's because of based on the father age and mother age. So we still have those old dimensions, but now like we are presenting this data in an X and Y axis. This might be like a little bit confusing because like again, why we have the two dimensions and then like X and Y doesn't make sense. Well, just wait for it a little bit. Because I'm sure it's going to start making more sense once we start adding more dimensions. So now here is like we have like each state. So like we have the state information, and I'm using a box plot and then visualize the variance for each state in terms of like a father age. And when we look at it, the District of Columbia is the most left-hand side, and Wyoming is the most right-hand side. And then so that means father age tend to be higher in the DC, and the father age tend to be lower on the Wyoming when they had babies. So that means I just brought like this state information. And then I just filter just the DC and the Wyoming data by using analytics leverage filter, which is the blue box. And then I assign the state column to the color by. Okay, so we have only DC and Wyoming. And then when we look at here, now it's kind of confusing, but like mother, father, the direction change, but basically the same thing. And the direction doesn't really matter. Like it's about like positioning to each other. So if we show only the Wyoming, and then you can see like Wyoming and most of the people are kind of like a right side, which is the opposite direction from the mother age and father age. That means they are younger on the mother and the father spectrum. On the other side, the DC, I just showing only the DC, then they are on the higher side of the mother and the father age. That doesn't mean like all of them are higher. I mean, some folks are still young, even the DC, but that's because like there's a variance. But we can see here is when you start adding the using the color, you can actually see, okay, so this is like basically like these two states are different on these two dimensions. Now, let's create, let's add more dimensions. So here, like I added the weight dimension, or like, sorry, the variable. Then it gets even more interesting. So here, let's say here in the variable columns, and then like I'm gonna weight and add the weight pound and run it. So now we have the kind of a different view, and then now here is father age and mother age and pointing the same direction. And then like a weight pound is pointing this directions. And it seems like the weight pound and the father and the mother age are not correlated because those are almost kind of across 90 degrees. And then like this y-axis is basically kind of similar to like weight pound. So like when you look at the y-axis, like a high or low, then it's more like this one is probably presenting the weight pound information, while the x-axis is presenting more like father and mother age information. And when you go to the component importance, the first dimension contains 60% of the information, almost 60% of the information. And then the second has a 33. Combine first and second, we have 91% of the original information or the variance of the data. So this data, like even though like we have 3 dimensions, or we used to have 3 variables, mother age, father age, weight pound, but now that we have X and Y, but we still have the original 91% of the information presented in this chart. And then not only that, like we can see, okay, which variables are correlated and which variables are not correlated at all. Okay, and then when you look at each folks, for example, let's say I'm going to bring the label. Oh yeah, label is here. So let's say here, what is this? So this is mother age and father age, pretty much kind of closer to the average, but a weight pound is, it says actually 0.90 because this column giving you the 3 information divided by underscore. So 0.9 pound, which is super light. And on the other hand, here, this one, 12 pound. Wow, that, I didn't even know that's even possible. It could be like a twins or triplets or something. But anyway, so 12 pound. And then, but when you look at the mother age and father age, 30 and 26, it's about the average, or like it's about like it's kind of like a middle ground. And when you go here, this is like a mother age and father age higher range, but the weight pound is 6.7, which is very kind of like a middle, close to the average, and so on. So now we have this, so this dot, each dot is each baby or each row, but and located based on this father, mother, weight pound information. So we have 3 variables, 3 columns, but we are using just 2 dimensions to visualize the data and understand the characteristics of the subjects, in this case, the babies. Okay, so that's one thing. And then, so now let's get back to the California election data. We look at a little bit quickly. So the California election, like we had like 17 ballots, and those are like too many ballots to understand like what are the states and how they're doing it, what are the characteristics of each, not the states, the counties. So what we can do is we can reduce the dimensions. So like let's run the principal component analysis again. And then the variable, I'm going to select all of them, all the Barrett measures. Oops. And then click OK, and then just run it. And at this point, we're basically seeing here is the component 1, which is the x-axis, contains 72 or 73% of the information or the variance of the original data. And then the PC2 is almost like a 15% of the variance or the information of the original data. And combine these two, we can go to the component importance. We have 87.6% of the variance of the original data. So that's pretty good. It's almost like a 90% presented in this two-dimensional X and Y space. And then now each measures are basically having this like a line. And then let's see, for example, this is like a corporate marijuana legalization and a corporate political spending advisory question. These two are almost like identical. It's all super correlated. And then this one, carry out bag charges and K-12 and a community college facility. These two are also very highly correlated. And then, so these are also though, like x-axis is pretty much kind of presenting these ballot measures. So like a higher the, on these measures, and then like on the x-axis wise, it's going kind of like left side. And then that means these states, I can bring the label on the county name column, and I'm going to just run it. And make it easier, in order to make it easier, I'm going to use this chart property, and then under the label text, I'm going to show the county name here, like that. Here we go. So now we see San Francisco, Marin, Santa Cruz, Alameda. Alameda is where the Oakland and Berkeley are. So if you're familiar with California, you can see like these are the liberal, very liberal counties. And then here is Modoc, Lassen, Shasta. These are like a very mountain side of California, northern side of mountain side of California. And it can be considered as a conservative. So these are the measures that makes, these right-hand side counties are scoring low. That means they support very low. That means they pretty much against on these measures. On the other hand, these side of the counties are supporting highly on these measures. And then there are other measures, though. For example, here are the freedom condom or legislative procedure requirements and so on. So these are kind of like, when you look at here, it's sort of like pouring these counties on this direction. So these counties seems like on most of this is like a, let's call it like liberal measures. On the liberal measures, almost like a kind of a zero line, so it's probably like a 50-50. But these are, when it comes to the adult freedom or legislative procedure requirements, they are supporting more a higher percentage. So, and then here there's a color by. So it turned out like this data has also the party name. Again, this is based on which presidential candidates they voted for. So by using this, we can sort of like estimate these counties more towards the Republican, more towards the Democratic Party. Then if I include that information, now these orange colored dots or the text are the Republican leaning counties, and these blue are Democratic leaning counties. So by just looking at this, and then we can see this x-axis is basically the difference between the Democratic and the Republican leaning counties. And then these two informations are very correlated to, the percentage of the yes on these measures. But when you look at here, these two measures, also, it can be like a death penalty vote approval too. These measures are not so much of the indicator in order to predict if this is going to be a Democratic counties or Republican counties, because even inside this like a blue counties, some of the counties towards going this way. But the interesting thing here is that these two measures, especially, basically their zero is right here. So that means all the count is closer to like a 0 on the y-axis. Basically, they don't care about these measures. Pretty much 50-50. So, I go either way. And then that result can be sort of like a look at confirmed by looking at this chart as well. So most of the states are not most of them, some of them kind of like a lower, but it's kind of like along like 0.5 line. And then there's some few states are very enthusiastically, not enthusiastic, but high percentage supporting this measure. So when you go to the analytics, you can see by using the color and then by using original dimensions, and we can start seeing some kind of patterns in that data. Okay, so the next one is the last example, which is I'm going to use what is it? Employee data. Here we go. So the employee data, I've been using this data in this series, so you might be familiar with already. But basically about employee, and each row is an employee, represent employee, and then like there are about like 27 attributes about age, about which department they're working for, how many years they work for, how much money they are making for, and that type of information. Then, so let's actually go directly there. So like let's open the employee data frame, and then go to the analytics. And then this is a heat map like we just saw. So like some of the measures are highly correlated. For example, job level, monthly income are highly correlated. And here the percent salary hike and performance rating also highly correlated and so on. We already can see, some of the measures or some of the variables are highly correlated to one another. And then now like let's create let's run the PCA. And here, like we can select all the numerical variables and click OK and then run it. And then now it tried to basically like find few like these two primary or principal components, PC1, PC2, and then each dot is an employee. So like based on this kind of a relationship presented by multidimensional these measures, and then but now they are actually presented in this two-dimensional space like X and Y. Looks like there are like two groups here, is like upper side and lower side, and then what separates upper and the lower is like this y-axis. So the y-axis, what is y-axis here? Is like there are two measures, like a performance rate, and then what is this? Percent salary. Percent salary hike and performance rate. So these two, and these two are actually, when you go here, this one. So the percent salary hike and performance rating 0.77 is a higher, relatively higher, highly correlated, and that's presented on the y-axis almost. And the x-axis, we see like total working years and the monthly income. This is a little hard to see, but job level, monthly income, total working years, age, those four are pointing in the same direction. So that means these four highly correlated to one another. And more importantly, so basically x-axis is the direction of either like higher salary or lower salary, or the higher working years or lower working years, while y-axis are sort of represented by these two. And then what are these? So is when you go to component importance, and the first component contains about 20% of information, original information, and then second component is 11% of the original information, or the variance of the original data. Combine the two, 30% of the information. So that's kind of like a small, unlike the previous two data set, we saw like first two components present like 80 to 90%. So this one is a little low, but still it's this chart here is useful because now like we can see like what are the variables are correlated to one another or not correlated to one another. So that means here's monthly income. And then, so let's say these two measures, like a performance salary rate, or what is that again? I keep forgetting this too. Where did it go? Wait a second. So performance rate and then salary hike. So these two measures probably don't matter like what in terms of like a salary, like a monthly income. It doesn't matter like, in terms of like a age, in terms of like working years. So because those are not correlated. And then, so for example, these people here scored a high point on the performance rate, for example, but their salary is sort of in a kind of a middle ground, average. So it probably doesn't really matter. Um, so that's what we get from here. In here, though, like we can actually, if these are not really correlated at all, and then we want to see like without that, like how what type of relationship we can find. Well, we can remove them. For example, and let's say salary, these two percent salary hike, performance rating, and then let's try to run again. And then now the age, total working years, monthly income, job level are more separated. Before was completely almost like going to the same direction because we had another dimension which is more uncorrelated. So here, left side again, this direction x-axis still presenting, sort of representing this type of information. When you look at here, though, there's a monthly income and a job level, and they are mostly same. And this is what, because we saw it already, it's almost like a too perfectly correlated in a way. So probably there's some kind of a business rule behind it. But age, total working years, not so much. I mean, it's correlated closer to them, but not like job level or monthly income. Okay, and then that means, so from here, here though, another thing is education. So education and monthly income, it's almost like a 90-degree. So in this organization, education, this is what did you study at the school, and that have almost like a no relationship in terms of like a higher salary or lower salary. So that's the kind of information we can see. Even like job involvement, how much these people like involved in the job. I don't know how they measure that, but that's also not much influence or like a relationship between relationship to the monthly income. And then last, I want to bring use the color information here, and then let's say bring the job role, like what type of the job role each employee are. And if I click on Run button, and then now like we have these 1, 2, 3, 4, 5, 6, 9 job types or job roles. And then you see here, it's kind of hard to see, but not a little bit when you pay close attention to it. Here, like you can see like a red color, like a lot of red color. And also right next to it is a kind of brown color. So the red is a manager and the brown is a research director. So these type of the people on kind of a left side, on the higher side of the monthly income, job level, total working years, even like age spectrum. On the other hand, this side is like a green or yellow green or pink. These are like research scientists, laboratory technician, and a sales representative. So these folks are kind of lower side. So again, you remember like all these lines, original measure, original variable, always starts from 0, x and y and 0. And then 0 is average. So that means these folks are kind of lower than the average, less than average in terms of like a monthly income and job level. And even like working years, and then probably like age-wise, and going opposite direction here. This is less pink, it's more green and yellow-green. So these folks are like probably like younger folks. So from this data, we can say sales rep and also laboratory technicians, they're probably like younger age, and then like a manager and a research directors and kind of higher or older age or something. So this is the kind of information we can get out of this. And then again, so not just the correlation, which variables are correlated to each other, that's useful too, or not correlated, but also by using the color and then like seeing each data point, and then we can start understanding like how we can describe this type of the category or this type of the subject or each data point, and then we can start understanding characteristics of this data. Okay, so go back to the slide. Oops. So to close, so why PCA? So, I think that this whole point of like I'm presenting this seminar is PCA or principal component analysis is super useful, especially like exploratory analysis phase. People tend to think this is like a dimensional reduction technique. So therefore, like, hey, I'm building machine learning algorithms. So I want to reduce the dimensionality or something like that. But to me, it's very useful when you're doing exploratory data analysis. You get the data, you want to understand, you want to find some patterns quickly, and then in an iterative fashion. And then, sometimes like this can be the first thing you can do. You just run a PCA, try to get understanding of like what are the columns, what are the variables correlated with one another, what are the variables not correlated, and how the each employee or customers or countries are sort of like scoring on those variables in a one single picture. So it's very useful in terms of like visualizing high dimensional data in a way like what our eyes can understand. And also like we can detect the patterns and characteristics that can be hidden in the data in a very better and deeper and simple way. Okay, so that's it to today's session.